Hello everyone. This is the first video I've made since the emergency notice. So let's see whether it will work for the rest of our semester. Alright, so on Tuesday, we got some basic ideas about the simple linear regression and reviewed some basic concepts about the simple linear regression. So, um, just in case you didn't pay enough attention to the contents on Tuesday, and some of you may just absent from the class for some reason. So this first video, I just repeat the same contents on Tuesday about the review of simple linear regression. So if you feel good about this part already, you can just escape this video to the next one. Alright, okay, so now let's start with the review. Okay, so we say that the simple linear regression is based on two quantitative variables. One is called the explanatory variable. The other one is called the response variable. Right, so for explanatory variable we call x, the response variable we call y. So we say x will affect y. The explanatory variable will affect the response variable. So for example, we say the study time and the exam score. Right, so we say the study time will affect the exam score. So we say the study time is the explanatory variable. The exam score is the response variable. Right, so similar idea for the example in our chapter notes. We want to study about the relationship between the sale price and the number of 12 packs sold of a particular brand of beer. So here we will have two variables. The x variable, which is the explanatory variable, is the price of the beer, right? And the number of 12 packs sold will be the y variable, which is the response variable, right? So here we have the price. We say this is the explanatory variable, which is the x. The price will affect the number of packs sold in the store, right? So this we call it is the response variable, which is the y. All right, and then let's look at the data set in the jump, right? So we have two columns. One is the price, which is the x. Sale is the y, which is the response variable. So we want to have the regression analysis. So we use the fit y by x. And x goes to x, y goes to y, and then okay. All right. So we see that the first thing shows for the output is actually this plot, right? So what is this plot? So this plot is called the scatter plot, right? So for scatter plots, we say it is the easiest way to show or describe the relationship between x and y. So we see that in the first step of regression analysis, scatter plot is always the first thing to show up. And then from the scatter plot, you can see, okay, it's kind of a decreasing linear relationship between the price and the sale, right? So it's not very curved, kind of linear, right? And then when the x increasing, the y will decreasing, right? So you kind of get the first idea about the relationship between these two variables. So we say the scatter plot is the easiest way to show the relationship. All right, and then the scatter plot will have three kinds, right? Okay, so it just draws three kind of scatter plots. Right, so for example, if I have the points like that, right, so it shows kind of a increasing trend, right? So for this kind of scatter plots, we call this shows the positive linear relationship. All right, and then if I have the points something like that, that means showing you a decreasing trend, right? So we'll have a negative linear relationship. But sometimes the points are everywhere like that, right? So you even cannot see it is positive or negative. So for this case, we say there's no clear linear relationship. All right. So we say the horizontal axis is always for the explanatory variable x, and the vertical axis is always for the response variable y. So x, y, x, y. You cannot change the order, because if you change the order, the increasing trend will change to decreasing trend. All right. So now let's come back to the output here. Alright, and now I want the jump to show me a regression line. Alright, so you see this red line is the regression line, and then the first output or first information you see from the regression analysis is this. Alright, so it says the sale equals to 2775 minus 248.9 times the price. So we say the price is the explanatory variable x, right? The sale is the y. So it will tell you what is the so-called the simple regression line, right? So the line is called the simple regression line, and this line also called the OLS regression or the OLS analysis. So what is this? This is short for ordinary least squared regression. Right, so actually these two are the same thing. It just gave another name, which is sounds fancy, right? But actually this name just tell you that's how this red line is obtained. Right, so we just choose the smallest distance squared sum to choose which line is the best line. And then the best line will be having the least squared distance. So we just call this line is ordinary least square regression line. Alright, and then again from this output we have this equation, right? So for this equation we call it is sample linear regression equation. Right, so we will have y hat equals to 2775 minus 248.9x. So here x is the price, right? Y hat is the predicted value of y, which is the number of packs sold, right? Alright, so we have we call it is the simple linear equation. Why we call it is equation, not model? So here, a model is to describe a population. So you have one population, then you will have one corresponding model. But for equation, that means whenever you have a random sample, you will have a equation based on the sample. So for one population, you can have many equations. Right, we will talk about this later. So here, remember, we call this is simple linear regression equation. And we have a general format of this equation, which is y hat equals to b0 plus b1x. Right, so here you need to interpret what is y hat, what is b0, what is b1. Alright, okay, so what is y hat? Y hat is the notation for the predicted value of y, which is for the response variable. Alright, so the predicted value of y, first you need to give the value of x, right? So that you can plug in into this equation and then calculate the corresponding predicted value of y. So the y hat is predicted value of y given a value of x. Alright, so next b0. Alright, b0 in math class, you need to know that b0 is called intercept, right? So here in this class, we call it is sample intercept. Why we call it is sample intercept? Because this intercept or this linear regression equation is obtained from the sample, right? So we call it a sample intercept. And then how to interpret this intercept, right? So what does this b0 mean? It means when x equals to 0, when x equals 0, that means this whole term will be gone, right? So if this whole term is gone, then the b0 is just the value of the predicted value for the y, right? So we say when x equals to 0, the value, the predicted value of y will just equals to our intercept, right? Okay, so next, what is b1? b1 means it is in math class, it is called slope, right? So here similarly we just call it is sample slope because it is obtained from the sample. So how you can interpret this slope? Here let's do a practice, right? So let's say when x equals to a, what is the the predicted value of y? Y hat will equals to, we just plug in the a into the regression line, so we have b0 plus b1 times a, right? So we give a notation that x value is a. Now I want to increase the x to a plus 1. I have one more unit or for the x value, and then I just calculate the predicted value again for the y based on the x value is a plus 1. So I just plug in b0 and b1 times, now it's a plus 1, right? So we use the multiplication rule, will be b0 plus b1 times a plus b1. Alright, so here notice this one, right? So b0 plus b1a is actually the predicted value for when x equals to a. And then we have a actual term, which is just the one we want to interpret, b1, right? Okay, so how we can interpret like this? We say when the x, which is the explanatory variable, increase by 1 unit. When x increase by 1 unit, the predicted value of y, which is y hat, will increase by the slope, which is v1. Alright, so let's look at the example. Right, so still our example about the beer sales and the price. So the price is x, the number of 12-pack beers sold will be the y, right? So we'll have this linear regression equation. And then we have the corresponding r square. We'll talk about that later. Alright, so now what does this B0 mean? So here B0 is 2775, right? Okay, first it is called the sample y-intercept. So we say theoretically, what does that mean? It means that it predicts the mean value of y when x equals to 0, right? Okay, so now think about one question. Does that have any practical meaning when x equals to 0? Can any store set the beer's price as $0? It is not possible, right? So that means it doesn't have any practical meaning for this interpretation. So what is the reason for this phenomena? Let's say do an example. We say when we getting older and older, our height is getting larger and larger when we are young, right? So here I randomly sampled from 2 to 16 years old kids. All right, and then what? And then based on the points, all right, based on the points, I get a regression line based on that. Now my question is, can you make the prediction for the age equals to 50? Can you use this line to make the prediction when age equals to 50? Yes or no? No, right? Okay, so no. Why? Because what? Because maybe after 18 years old, your height will not getting larger and larger with this trend anymore. It will keep the same. When you're getting older, your height may be getting smaller and smaller, right? So that means this regression line is only based on this range, your sampled range. So that means out of this range, you don't know whether it will keep going up or keep the same or even decreasing, right? Out of this, you don't know whether it is increasing very fast or not as fast as this one. You never know about it, right? Because this regression line is just based on this sample. So when we make the prediction, we cannot make the prediction for the future. We can only make the prediction for whatever you have already collected, right? So for example, you can make the prediction for 5.5 years old, right? Then you can go to the line and then you can cross it with the y-axis. So this one will be the prediction for 5.5, right? So for this case, if you do this prediction, if you make the prediction based on this regression, you will make the serious mistake. So here we call this serious mistake as extrapolation. It is very common but very serious problem mistakes. So we gave a special name on it. See how important it is? All right. Okay. So let's come back to our case, right? So we see that the sample is collected is about from 7 to 11, right? Okay, so actually you can only make the prediction in this range. You cannot make the prediction when x equals 0 because 0 is not in this range, right? So for this case, how you can interpret this b0? First, b0 is the sample y-intercept, and then theoretically it predicts the mean value of when x equals 0. But we do not have practical meaning for x equals to 0, right? Because we cannot have the extrapolation mistake, right? So we say this y-intercept doesn't have any practical meaning. All right, next one for the B1, right? So first, what is B1? The B1 is the positive 248.9 or negative 248.9 will be the whole thing here, right? So remember our format is y hat equals to b0 plus b1x, right? So that means here the sign is always 0. So if here is negative, that means your b1 is negative, right? So this is the case b1 is negative 248.9. So first, it is the sample slope, right? And then we say when x increase by 1 unit, y will increase by the slope, right? So now we have the detailed case. So we say for each $1 increase in the price of a 12-pack, our predict sales decreases by 248.9 units on the average. Alright, so here there are several things. The first thing is you need to replace the x with the detailed variable, which is the price, right? And another thing is when you say the unit, you cannot just say unit. We have the own unit for this detailed case, which is the dollar, right? Okay, and then the y, what is y? Y is the predict sales, right? And actually it's y hat, right? So it is the predict sales will increase by b1. That means theoretically we say y hat will increase by negative 248.9. But for this case, it is not um, it is not a good way to say increase by a negative number, right? So what we say y hat will decrease by the positive part. So we say the decrease by 248.9 units on average. All right, so combined together, we can say when the price increase by $1, the predict y, which is the predict sales, will decrease by 248.9 units. Right. Another thing is on average. Alright, so we say that the predict sale is the thing that's not for a single one, right? So it will be for any, for example, like this. Okay, for this case, right? So for all of these stores, have the price is 9.99, right? But their Y are different, right? So that means they this B1 is not just for single observation. It is actually the slope for all of these with the same price. The stores Y will have these many. Alright, okay, so it will be on average, not just for one. Right, so I think it's pretty important to understand how to interpret this B1 correctly. Right, so first you need to make the detailed x variable and y variable. The second, you need to change the unit. Right, and then the last thing is you need to decide it is increase or decrease. And then the last one, don't forget about the last on average. All right, so we talked about how to interpret these three, but when we look at the output, the next one, summary of fit table, the first information is r square. Alright, so let's talk about r square. But before we talk about r square, we want to talk about the r. Right, so what is r? The r is called the correlation. Right, so what is correlation then? It mirrors the strength. It mirrors the strength of the linear relationship between x and y. Alright, so here be careful. R can only mirror the linear relationship. It cannot mirror other linear, may not mirror other relationships. So for example, if I have the points like this, right? So actually it is clear to see that these points follow a pattern, right? It is a curved pattern. So is there strong relationship between x and y? Yes, right? Because they follow a very strong pattern. That means there must be some relationship between x and y, right? But is there any strong linear relationship between x and y? The answer will be no. Alright, so that means for this part is decreasing, for this part is increasing. So overall, you cannot determine it is decreasing or increasing, right? So there is no linear relationship between these two variables. So for this case, if you calculate the r for this relationship, it will be very close to 0. Alright, so that means the other way. So when r equals 0, it doesn't mean that there's no relationship between x and y. It only means there's no linear relationship. Alright. Okay, so this is the correlation, and for the correlation we have several properties. Right, the first property, it always have a range from -1 to 1 inclusive. Right, so if we draw the picture, it is from -1 to 1, middle with 0. Right, so we say when r equals to 0, we have the strongest linear relationship. The same thing when r equals to -1, we also have the strongest linear relationship. So you may ask which one is stronger, since both of these two are strongest. They have the same strength, but why this is +1, this is -1? when r equals to positive 1, that means we have this direction, which is the positive linear relationship. When r equals to negative 1, that means we have this direction, the decreasing direction, right? So we have the strongest negative linear relationship. Right, so both of these two are strongest. This negative sign is just because of their directions. All right, and then in the middle, we say when r equals to 0, we have the weakest, again, linear relationship. Right, so for example, if I have r1 is 0.8, I have r2 is negative 0.9. All right, okay, so which one has stronger relationship? Which one has the stronger relationship? Will be r2, right? So this negative sign doesn't mean that 0.8 is larger than negative 0.9. It just to show you the direction. It is the negative direction. This is the positive direction. But which one has the stronger relationship? R2, because 0.9 is larger than 0.8. All right. So this is the first property of R. And let's talk about the second property. R has no unit. Alright, so this is easy to understand. We cannot write R equals to 0.64 kilograms. Right, so it doesn't have any units. R just have the value. It's the value. It is mere the strength. Right, so R is just a 0.64 for this example. Alright, next property. We say, what if R equals to 0.99? It is a very high correlation, right? The biggest is 1, right? So it is very, very close to 1. So we say it is very high correlation. Can we say that the x cause y? No, right? So here we have a very famous sentence. We say a high correlation doesn't mean the causation. Alright, so the high correlation only means what? Only means x and y are strongly related. Alright, so we can only say the age and the height are strongly related, but I cannot say the age causes the height. Right? We can only say the age affects the height, but cannot determine the height. Alright, so here we say a high correlation doesn't mean the causation. And the last one we want to talk about the correlation will be the effect of outliers. We say the outliers will affect the correlation. Alright, okay, so we have two cases. Right, so for example, I have these points, and then based on these points, I have a regression line. Alright, okay, and then I have a outlier far away here. Alright, so we say this outlier is on the line. Right, so if the outlier is on the line, then What about the correlation? The correlation will be stronger or weaker? The correlation will be stronger because it shows the direction of the original regression line, right? Okay. The other way, if I have another point off the line, we say the outlier is off the line, it's not on the line, then this outlier make the correlation weaker. Right, so the other way, if you remove this outlier, so this outlier make the correlation stronger, but if you remove this outlier, the correlation will be weaker. For this outlier, if you remove this outlier, the correlation will be stronger. Okay, now my question is, do you delete this outlier? Yes. Alright, do you delete this outlier? Yes. Alright, so for any outliers, you need to delete them before any data analysis. Why? It doesn't matter the outlier is on the line or off the line. The outliers affect the true correlation. Alright, so we say the outliers affected the correlation, so we need to remove the outliers before any analysis. Alright, so until here we have talked about the properties of the correlation. Right, so again, when you look at this output, it doesn't show you the what is R, but instead it talk about what is R square. So what is R square? We say it is just the square of R, right? So we say R is 0.8, then what is R square? 0.8 square, which is 0.64. Right? Okay, so R square, actually the value of R square is just a 0.64. But why in the output it doesn't have the R, instead they have the R square? Because R square has its own meaning. It's very important meaning for the linear regression. It shows the proportion of variation in Y, actually is observed variation in Y that can be accounted by X or by modeling of X. Alright, so here, what does that mean? It's a long definition, but you need to remember them. Alright, so now look at our data. Right, so the cell is the Y, right? So we see these ones, these values are observed Y values, right? And then we see these observed Y values have variations. They are different values, right? So we say these values are different. So we say the total observed variation in Y, right? So actually we want to study about where does these variations come from, right? Why these Y values are different. So actually these total variations in Y can be divided into two parts, right? The first part we say based on our regression, y hat equals to 2775 minus 248.9x, right? So based on our regression, we have, if you have different x values, then of course you will have different y values, right? So actually, the first part of variation, that's the variation in y, it actually is just can be accounted by x or by modeling, right? So since you have different x values, then you will have different y's. So this is the first reason for why these y values are different. All right, so this is just because of the different x values. But now if you look at the data, you see these stores are all have the same price, 9.99. But if you look at their corresponding y, they are not the same. They still have some different, still have different values, right? So why they still have the different values? Because the second part of the variation, some other variations, we say some other variations in y is just caused by the random error. So what is random error? Since they have the same price, but these stores are different stores. So when you randomly select the stores, you cannot control that every store have exactly the same thing. Every store is identical, right? So these are called the sampling error or just a random error. All right, so now think about one question. You want this part of variation in y as small as possible or as big as possible. You want this part as big as possible, right? So that means I see some variations in the observed y. I want all of these different values just because I have different x values. I want this part of variation just by the random error to be as small as possible, because I don't want these random fluctuations, right? That I cannot model it. I just don't know why, right? Because every store has their own story, right? So when you make the regression, I want this part as big as possible. So here I just use r squared to measure it. So we say r squared is the proportion of the observed variation in y that can be accounted by x. Alright, so it's just this proportion. So for example, if r is 0.8, then what is r squared? R squared is 0.64. So how you interpret this 0.64? It means 64% of the observed variation in y can be accounted by x or modeling by x. That means the other 36% will be just because of the random error, right? Okay. So this is the way how you interpret the r square, right? We'll talk about this all through the simple linear regression and even the next chapter, which is the multiple regression, right? We'll talk about r square. The r square is very, very important to decide whether this regression is good or not. Alright, so since our r is larger equals to -1 less equals to 1, that means r squared also have the range larger equals to 0 less equals to 1. So we say when r squared is closer to 0, that means we have very weak linear relationship, right? So when r squared is closer to 1, That means more proportion, almost 100% of the variation just because of this regression, right? So that means this regression is strong. All right. So here we just reviewed all the concepts about the simple linear regression. And if we have any more other topics we'll cover it later, we'll talk about that in that section. Right, so now that's enough for the review of the simple linear regression. In the next video, we'll talk about some new contents for this chapter. All right, so see you in the next video.